Hello everyone, in this video I am going to explain about Prim's algorithm. The output of Prim's algorithm should be a minimum spanning tree. The properties of minimum spanning tree will also be applicable for Prim's algorithm. The first property is total number of vertices. The total number of vertices are nothing but here initially we have 6 vertices in this graph. And finally, after constructing minimum spanning tree, there should be total of 6 vertices. This is the first property. Second property is total number of edges are equal to v minus 1, where v is nothing but the total number of vertices present in the graph. And the third property is it should not form a cycle. And the fourth property is the total cost should be optimized. The minimum cost should be generated in the minimum spanning tree. Let us solve this problem by applying Prim's algorithm step by step. The Prim's algorithm starts with vertex, that is single vertex. In this graph, there are total of 6 vertices. I am considering the vertex 5 and it will be considered as source vertex. So now 5. I have to draw 5. Now 5 is connected to 4 and 1. 4 and 1 will become the adjacent vertices to 5. So 5 to 4, the cost associated with edge is 9. 5 to 1, the cost associated with edge is 4. Now prime and 4, two values I have to always go with the least value. 4 is less compared to 9. So I am including 5 to 1 edge. So now let us draw 5 to 1. So 5 to 1, what is the cost associated with it? With this 4. Now 1, what are the neighboring nodes? 1 to 2, 1 to 4, 1 to 5. Let us have a list here, visited nodes. Now 5 is visited. I cannot consider visited vertex. So I have to exclude 5. So what are the remaining options I have here? 1 to 4, 1 to 2. So 1 to 4, what is the total weight here? 1. What is the weight associated with 1 to 2? 2. Now I have to consider the least cost. So 4 to 1. I want to include edge 1 to 4. Let us draw here. So it is not a directed, it is undirected graph. Now 4 is connected to 3, 4 is connected to 2 and 1. 1 is already visited. Now 1 will become visited vertex. Now I should not consider 1. So what are the other options I have? 4 to 3 and 4 to 2. What is the cost associated with what? 4 to 3, it is 5, and 4 to 2, it is 3. So least value is 3, but before including the edge 4 to 2, let us check whether there is any edge with least value, that is less than 2. Okay, so now less than 2, here less than 3 is 2. 1 to 2, I have 2. And 4 to 1, I have 1, which is less than 3. But I have already included in the graph. I am excluding it. 1 to 2, the value is 2. So which is less than 2, I can include it. So now, let us include 1 to 2. What is the cost associated with this? 2, and here is 1. Okay, so now 1 to 2 and 2 is connected to 3, 1, 4 and 6. 1 is already visited. Now I have 3 options, 1 to 4, 2 to 3 and 2 to 6. If I include 2 to 4, that is the least value 3, least cost weight, it will form a cycle. Okay. It will form a cycle. so I should not include it. Okay. Now, what are the remaining options I have here? 2 is connected to 3, 2 is connected to 6. What is the cost associated with 2 to 3? It is 3. 2 to 6, 7. 3 is less compared to 7. So now we have to include 2 to 3. Let us take 3. So 2 to 3. What is the cost? 3. And now let us see 3 is assorted. Now 2 is visited. Now 2 will become visited. We have to repeat this until I visit all the vertices. Okay, now 3 is connected to 6, connected to 4 and 2. If I include 3 to 4, it will form a cycle here. So 3 to 4, it will form a cycle, so I should not include it. And 3 to 2 already included, so already visited. So now what is the other option I have? 3 to 6. But 3 to 6, the cost is 8. Let us see if whether there are any edges in the graph which are less than 8. Okay. So now 4 to 5 to 1, 1 to 4, 2 to 3, 1 to 2, and these are the included vertices. What is the next value? If I include 4 to 2, it will form a cycle. 4 to 3, it will form a cycle. Now 5 to 4, it will form a cycle. So what is the remaining edge here? 2 to 6. Now let us add here 2 to 6. So what is the cost associated? So 7. So this is the final graph. Final minimum spanning tree. Let us redraw this. To calculate the final cost, I have included 5 to 1, 1 to 2, 6, and now 4. Next 3. Now cost is 4, and here 1. This is 2, 3, and 7. This is the final minimum spanning tree. Let us calculate the total cost associated with this. Let us check whether it is satisfying all the properties of minimum spanning tree. The first one is it should not form a cycle. There is no cycle here. And the second one is total number of vertices. How many vertices are there? 1, 2, 3, 4, 5, 6. So, second condition, that is total number of vertices, is also satisfied. And the third one is total number of edges, e minus 1. So 6 minus 1, which is equal to 5. 1, 2, 3, 4, 5. Total number of 5 edges are available. So third condition is also satisfied. Now let us calculate the total cost in minimum spanning tree. So what is the total cost here? 4 plus 1 plus 2 plus 3 plus 7, which is equal to 70. Okay. So what is the cost of input graph? So we have listed all the vertices. Already visited. Now let us calculate the total cost. is equal to 9 plus 4 plus 1 plus 2 plus 3 plus 5 plus 3 plus 7 plus 8, which is equal to 42. Okay, so 42 initially the total cost is 42 and now it has been reduced to 70. This is the overall cost. Minimum spanning tree cost. $70. So this is the way we have to calculate the total cost and we have to construct minimum spanning tree. So let us see what are the edges we have included, what are the edges we have excluded. So 5 to 1 included, 1 to 2, 2 to 6, 4 to 1, 2 to 3. And excluded edges are 5 to 4, 4 to 3, 4 to 2, and this I have included. So also included. So this is Prim's algorithm. Thank you.